is causal inference and statistics, and we are on question 4.4.1. Okay, and so there's 3 parts here, and so we'll just look at the questions as we come to them, but roughly speaking, what we're trying to do is we're going back to the data set way back in chapter 1, where we were looking at the effect of taking a drug or not taking a drug in men and women. Okay, and so so at that time we had a DAG that looked something like this, where recovery was Y, Z was the sex of the person, and X was taking the drug or not taking the drug. Okay. So that's the basic setup, and so let's look at part A. Okay. So so here we're trying to prove that if X is binary, in this case taking the drug or not taking the drug, then the effect of treatment on the treated, or ETT, can be estimated from both observational and experimental data. And we're given the hint of trying to decompose the expected value of Y with the counterfactual value of X here. Okay. So what do I want to say about this before we start? Okay, so the thing that I want to say about this before we start is that this is meant to be a binary depiction of some of the principles that were demonstrated in example 4.4.1. Namely, if there is a way to close the back door, then we should be able to get an estimate. So so if there's a backdoor, say between trained and hired, but in this case it's going to be between drug and recovery, and if we can close the back door, either experimentally or statistically, then we should be able to get an estimate of the effect of training on hired or drug on recovery. Okay, and therefore we can find the ETT in that scenario, specifically because we have a backdoor. And so here we're just going to explore that, but using binary data. People recovered or they didn't recover. They took the drug or they didn't take the drug. They're male or they're female. Okay. So what this question is trying to get us to do is to find an expression for the ETT that does not invoke these counterfactual terms here. All right. And it gives us the hint, of decomposing this into this. And so let's kind of start. Let's start there. Okay. So first of all, why can we decompose this into these two terms here? Well, this works here in the case of binary data because Y is only occurring under one of two values for X, right? When X is one value or the other value. Okay, so so that's why we can use this decomposition here. All right, so so now when X prime is 1, then we get that the counterfactual value is the expected value of Y when X equals 1. Okay, so so we get from here to here by the consistency rule. Okay, in other words, the counterfactual value is the same as the observed values for for the predictor variable here X. Okay, and so again, this is just the consistency rule that's mentioned in the example and given in the chapter. Okay, okay. So in other words, we already have this first term here, okay, where X, the counterfactual value of X is equal to, the observed value. So that means that we're left with trying to find, a value for this expression here. Or in other words, the expected value of Y for a counterfactual value of X when the observed value of X, differs from the counterfactual value. Okay, so and notice that this aligns over here. again, the reason that this is tricky is because whereas when the counterfactual value lines up or is equal to the observed value, we have data already for that outcome, but here we have we don't have observations for the counterfactual value. Okay. So so let's try to find an expression for this guy, right, which is going to ultimately correspond to this guy, right, again, where the counterfactual value does not match the observed value. Okay. And so the way that I'm going to do that is I'm going to take this expression here, and I'm just going to solve for the term of interest. So I'm going to subtract this over and then divide by this. Okay. And so I come away with that. All right. But we already, for that counterfactual term right there, we already have an expression for that, right? Which is just here. We've already found that, right? It's just the expression we already found earlier by the consistency rule. Okay, so we have that. Okay, so now this is a general form of the expression, right, where I'm just using x and x prime. But here we have that that x prime equals 0 and x equals 1. So just entering those into the equation, I get this. Okay. Right. So in other words, again, for ETT, this second expression is equal to this right here. Okay. So now if I plug that into the ETT, right? So here's my expression for ETT that we're familiar with. We already have an expression for this by the consistency rule, and then our expression for for the counterfactual value differs from the observed value, we have this. Okay. So right now we've eliminated some of the counterfactual notation, but we still have that guy right there. Okay, and so we need to see if there's a way that we can change this into a non-counterfactual expression. So how might we get this? Well, this is where the whole backdoor trick comes in. Okay, so again, what we're asked to find is, what is the expected value of y when x equals some particular value? Well, that is the same thing as asking what is the value of y under the do operator for x, because by the do operator we block the backdoor, we condition on z, blocking the backdoor, and then we get the expected value for y given x, or for any particular value of x, right? And so that's exactly what we get right here, right? So in other words, this expression, because we can close the backdoor, is equal to this expression. Okay, and for the do operator, as long as we can condition on the variables that would close all backdoor paths, well, then we have a counterfactual free expression for ETT. Okay. Okay. Well, now that we have that expression, we're going to try to use that expression with the data given here in table 1.1. So I won't bore you with all of the math, right? It's really just finding the appropriate table or appropriate values in the table, plugging them in, and pushing through, doing all the calculations. Now, I am doing a lot of estimation here, or rounding, just I think to make the math easier to follow as you go from here to here, right? But each one of these steps, there's some rounding error that's taking place. So, if you do the rounding as I did, you get, you get about 0.06, so there you go. Now what we're going to do in the next part, is we're going to apply the expression that was given in the book and that we briefly talked about in the previous video for example 4.4.1, where is it? This expression, which is the modified backdoor adjustment formula for counterfactuals. Okay, and so we're actually going to apply this as an alternative way of trying to find the ETT. Okay, so again, our ETT is, no, that's not right. Okay, so our ETT is this, and we already have an expression for that first part by the consistency rule. And so now we want to find an expression for this second part. Okay, so it's the expected value for all of this. Okay, so this is that modified backdoor adjustment rule, right? Which again, if you scroll up, you can find. And because we want expectation, right? So this is the, this is deals in probabilities. We need to multiply those probabilities by the different values of y, sum over those y's here, right? That gives us the expectation. Okay. And once again, I'm not, you can go through step by step here for yourself. But what you notice when you do this, you come out with approximately the same answer. These should be exactly the same answer, but again, because in how I'm trying to demonstrate the math, I'm accepting a lot of rounding error. But you come out with what should be the same answer. It's just when you when you apply the rounding errors as I have here, you come out with something close to this. But this and this are actually the same. I did it without the rounding errors. It's harder to follow because you make these big fractions that you're trying to rationalize and all this. So, but anyway, so just to recap what we did in these last two parts, we found the expected value of treatment in the treated, or the effective treatment in the treated, in two different ways. One using the modified backdoor formula, and the other one where we just derived counterfactual free expressions for all the terms in the ETT. And again, the thing that allowed us to do a lot of this in both cases was the fact that we could close the backdoor paths here, Z, right? With the modified backdoor adjustment, that's what the summing over all possible values of Z is. Okay, well, yeah, we'll call that good. Bad ending. Okay.